In this video, we're going to cover section 1.19.2, the Franck-Condon principle. The Franck-Condon principle is often used to help us explain why we observe structure in our spectra. But before getting into those details, let's introduce some of the fundamental aspects of the Franck-Condon principle. First, nuclei are much more massive than electrons. For example, the mass of a proton is approximately 1,000 times that of the mass of an electron. As a consequence, electron motion is much faster than nuclear motion. Electron motion occurs on a timescale of femtoseconds to hundreds of attoseconds, whereas nuclear motion occurs on a timescale of picoseconds to tens of femtoseconds. As a result of this, an electronic transition takes place while the nuclear geometry of a molecule is essentially fixed. So one question we will address in this section is, how is the Franck-Condon principle important in experimental measurements? And what I hope to show you is that it helps to explain vibronic structure of absorption and emission spectra, the relative intensities of vibronic bands, and the relative rates of radiationless transitions. This figure represents the Franck-Condon principle for radiative transitions of a diatomic molecule. Radiative transitions tend to occur at nuclear geometries corresponding to spectroscopic minima in both the ground state and excited state surfaces. In this figure, we're looking at three different examples of radiative transitions between the ground state R and the electronically excited state R star. And the main difference between these three different examples is the relative positioning of the excited state minima with respect to the ground state minima. In case A, the minima lie directly over one another. As a result, there is no excess vibrational energy produced by this electronic transition. And we see the largest overlap between the 0th level of the ground state and the 0th level of the excited state surface. In case B, the minima are slightly shifted with respect to one another, such that the largest overlap occurs between the 0th level of the ground state and the 1st level of the excited state. In this particular transition, some excess vibrational energy is produced. And in case C, the minima are significantly shifted with respect to one another, such that the largest overlap occurs between the 0th vibrational level of the ground state and the 5th vibrational level of the excited state. In this example, a significant amount of excess vibrational energy accompanies the radiative transition. Again, radiative transitions tend to occur at nuclear geometries corresponding to spectroscopic minima in both the ground state and excited state surfaces. As shown in the previous figure, in case A, where the minima lie directly over one another, we saw that the largest overlap occurs between the 0th vibrational levels. This is typical of a pi to pi star transition of a rigid aromatic hydrocarbon, where no excess vibrational energy is produced by the transition. However, in case B, where the minima are slightly shifted with respect to one another, we saw that the largest overlap was between the lowest vibrational level of the ground state and the 1st vibrational level of the excited state. This is typical of an N to pi star transition of ketones, where some excess vibrational energy is produced during the transition, resulting in that CO stretch. And in our third example, case C, where the minima are significantly shifted with respect to one another, we saw that the largest overlap was between the 0th level of the ground state and the 5th level of the excited state. This is typical of a pi to pi star transition of an alkene, where there is a significant amount of excess vibrational energy produced by the transition, resulting from not only the pi bond breaking, but the twisting that occurs about that new sigma bond. So in summary, for cases B and C, the electronic transition initially produces an R star state that is both a vibrationally excited and electronically excited species. We refer to this state as a vibronic state, and we refer to the transition as a vibronic transition. Now, in quantum mechanics, the most probable electronic transitions are those that possess vibrational wave functions that look most alike at the instant of the electronic transition. This similarity is given by the overlap integral of the vibrational wave functions of the two states, and it's often called the Franck-Condon integral. The square of this integral is called the Franck-Condon factor. So the larger the Franck-Condon factor, the greater the net constructive or positive overlap of the vibrational wave functions, and the more probable the vibrational electronic or vibronic transition. Thus, the Franck-Condon factor governs the vibronic structure of absorption and emission spectra. The Franck-Condon factor also governs the intensities of vibrational bands in absorption and emission spectra. That is, the most intense transitions or bands will exhibit the greatest overlap. So let's look at some examples. So in this example, we're looking at an absorption process between our ground state minima and our excited state minima. And similar to what we discussed for case C, we observe a significant shift in the excited state minima with respect to the ground state minima. As a result, we expect that the greatest overlap will be between the 0th vibrational level of the ground state and some higher vibrational level of the excited state. In this example, we see that the best overlap occurs between V equals 0 and V equal 4. And that's shown in the absorption spectrum above, where the highest intensity is going to be the transition between vibrational wave functions that have the greatest overlap. And so our V equals 0 to 4 transition is the most intense transition within this absorption spectrum. In this example, this is more closely related to our case A, in which the excited state minima lies directly above the ground state minima. So in this example, we would expect the greatest overlap of the vibrational wave functions associated with the 0th level of the ground state and the 0th level of the excited state. As a result, the most intense transition in this absorption spectrum will be observed between the 0th levels. And the Franck-Condon factor will be smaller for transitions between the 0th level of the ground state and higher vibrational levels of the excited state. And in this example, similar to what we saw for case B, the excited state minima is slightly shifted with respect to the ground state minima. As a result, we would expect that the greatest overlap occurs between the 0th vibrational level of the ground state and the 1st or 2nd vibrational level of the excited state. In this example, the most intense transition will be between the 0th and the 2nd level of the excited state minima. Transitions to lower vibrational levels or higher vibrational levels in the excited state minima will result in less intense absorption bands due to a smaller Franck-Condon factor because there is less overlap between the vibrational wave functions. In addition, we can also apply the Franck-Condon principle for emission spectra. We see in this example where again the excited state minima is slightly shifted with respect to the ground state minima, that the most probable transition will occur from the 0th vibrational level of your excited state minima and the 2nd level of the ground state minima. So in a similar fashion, similar way to what we just saw, the most intense transition will be found between the 0th and the 2nd, and transitions to lower vibrational levels in the ground state or higher vibrational levels in the ground state will be less intense. Similar to radiative transitions, radiationless transitions are also most probable for nuclear geometries at which two surfaces, a minimum and a maximum, come close together in energy. For example, let's consider internal conversion between the S1 and the ground state S0. Internal conversion will occur between the lowest vibrational level of the S1 state and some higher vibrational level of the S0 state. In this example, we're looking at the overlap between the vibrational wave functions of the 6th vibrational level of the ground state, that is R, and the 0th vibrational level of the S1 state, R star. And as you can see on the left-hand side, we have a poor net positive overlap between those two vibrational wave functions. As a result, we would expect the rate constant for internal conversion to be very low in magnitude and the quantum yield to also be quite low. However, when the excited state minima is significantly shifted with respect to the ground state minima, we observe that the vibrational wave functions overlap quite well between the 0th vibrational level of the excited state, the S1 state of R star, and the higher vibrational level, in this case, the 6th vibrational level of the ground state of R. As a result of this large Franck-Condon factor, we would expect the quantum yield for internal conversion to be quite high and the magnitude of the rate constant for internal conversion to be quite large. So in conclusion, we can use the Franck-Condon principle to explain the vibronic structure that we observe in absorption and emission spectra. We can use it to explain the relative intensities of vibronic transitions. And finally, we can use the Franck-Condon principle to explain the relative rates of radiationless transitions. So in conclusion, we can use the Franck-Condon principle to explain the vibronic structure that we observe in absorption and emission spectra. We can use the Franck-Condon principle to explain the relative intensities of vibronic transitions. And finally, we can use it to explain the relative rates of radiationless transitions. So if you have any questions about the Franck-Condon principle or any other material that we've covered in this course, by all means, please send me an email. Thank you.